Hello, welcome to the video lecture series on digital image processing. Now, we start discussion on the frequency domain processing techniques. Now, so far you must have noticed that this mask operations or the spatial domain operations using the masks, whatever we have done, that is nothing but a convolution operation in 2 dimension. So, what we have done is, we have the original image f x y, we define a mask corresponding to the type of operation that we want to perform on the original image f x y, and using this mask the kind of operation that is done, the mathematical expression of this is given on the bottom, and if you analyze this, you will find that this is nothing but a convolution operation. So, using this convolution operation, we are going for spatial domain processing of the images. Now, we have already seen during our earlier discussions that a convolution operation in the spatial domain is equivalent to multiplication in the frequency domain. Convolution in the spatial domain is equivalent to multiplication in the frequency domain. Similarly, a convolution in the frequency domain is equivalent to multiplication in the spatial domain. So, what we have seen is that if we have a convolution of say 2 functions f x y and h x y in the spatial domain, the corresponding operation in the frequency domain is multiplication of f u v and h u v, where f u v is the Fourier transform of this spatial domain function f x y and h u v is the Fourier transform of the spatial domain function h x y. Similarly, if we multiply 2 functions f x y and h x y in the spatial domain, the corresponding operation in the frequency domain is the convolution operation of the Fourier transforms of f x y, which is f u v, that has to be convolved with h u v. So, these are the convolution theorems that we have done during our previous discussions. So, to perform this convolution operation, the equivalent operation can also be done in the frequency domain if I take the Fourier transform of the image f x y and I take the Fourier transform of the spatial mask, that is h x y. So, the Fourier transform of the spatial mask h x y, as we have said that this is nothing but h u v in this particular case. So, the equivalent filtering operations we can do in the frequency domain by choosing the proper filter h u v, then after taking the product of f u v and h u v, if I take the inverse Fourier transform, then I will get the processed image in the spatial domain. Now, to analyze this further, what we will do is, we will take the cases in 1 dimension and we will consider the filters based on Gaussian functions for analysis purpose. The reasons we are choosing these filters based on Gaussian function is that the shapes of such functions can be easily specified and easily analyzed. Not only that, the forward transformation, the forward Fourier transformation and the inverse Fourier transformation of Gaussian functions are also Gaussian. So, if I take a Gaussian filter in the frequency domain, I will write a Gaussian filter in the frequency domain as h u is equal to some constant a e to the power minus u square by 2 sigma square, where sigma is the standard deviation of the Gaussian function. And if I take the inverse Fourier transform of this, then the corresponding filter in the spatial domain will be given by h x is equal to root over 2 pi a e to the power minus 2 pi square sigma square x square. Now, if you analyze these two functions, that is h u in the frequency domain and h x in the spatial domain, you find that both these functions are Gaussian as well as real. And not only that, both these functions, they behave reciprocally with each other. That means, when h u has a broad profile, this particular function h u in the frequency domain, it has a broad profile, that is, it has a large value of standard deviation sigma. The corresponding h x in the spatial domain will have a narrow profile. Similarly, if h u has a narrow profile, h x will have a broad profile. Particularly, when the sigma tends to infinity, then this function h u, this tends to be a flat function, and in such case the corresponding spatial domain filter h x, this tends to be an impulse function. So, this shows that both h u and h x, they are reciprocal to each other. Now, let us see what will be the nature of these functions, nature of such low pass filter functions. So, here on the left hand side, we have shown the frequency domain filter h u as a function of u, and on the right hand side, we have shown the corresponding spatial domain filter h x, which is a function of x. Now, from these filters, it is quite obvious that all the values, once I specify a filter h u as a function of u in the frequency domain, the corresponding filter h x in the spatial domain, they will have all positive values. That is, none h x never becomes positive negative for any value of x. And the narrower the frequency domain filter, more it will attenuate the low pass frequency components, resulting in more blurring effect. And if I say make the frequency domain filter narrower, that means the corresponding spatial domain filter or spatial domain mask will be flatter. That means the mask size in the spatial domain will be larger. So, this slide shows two such masks that we have already discussed during our previous discussion. So, this is a mask where all the coefficients are positive and same, and in this mask the coefficients are all positive, but the variation shows that it is having some sort of Gaussian distribution in nature. And we have already said that if the frequency domain filter becomes very narrow, it will attenuate even the low frequency components, leading to a blurring effect of the processed image. Correspondingly, in the Highpass, correspondingly in the spatial domain, the mask size will be larger, and we have seen through our results that if I use a larger mask size for smoothing operation, then the image gets more and more blurred. Now, in the same manner as we have said the low pass filter, we can also make the high pass filters again in the Gaussian domain. So, in this case, in case of Gaussian domain, using the Gaussian function, a high pass filter h u can be defined as a into 1 minus e to the power minus u square by 2 sigma square. So, this is the high pass filter which is defined using the Gaussian function. If I take the inverse Fourier transform of this, the corresponding spatial domain filter will be given by h x equal to a into delta x minus the same square root of 2 pi into a into e to the power minus 2 pi square sigma square x square. So, if I plot this in the frequency domain, this shows the high pass filter in the frequency domain. So, as it is quite obvious from this plot that it will attenuate the low frequency components, whereas it will pass the high frequency components, and the corresponding filter in the spatial domain is having this form, which is given by h x as a function of x. Now, as you note from this particular figure, from this particular function h x, that h x can assume both positive as well as negative values. And an important point to note over here is, once h x becomes negative, it will remain negative, it does not become positive anymore. And in the spatial domain, the Laplacian operator that we have used earlier, the Laplacian operator was of similar nature. So, the Laplacian mask that we have used, we have seen that the center pixel is having a positive value, whereas all the neighboring pixels have the negative values. And this is true for both the Laplacian masks, if I consider only the vertical and horizontal components, or whether along with vertical and horizontal components, I also consider the diagonal components. So, these are the two Laplacian masks where the center coefficient is positive and the neighboring coefficients, once they become negative, they will remain negative. So, this shows that using the Laplacian mask in the spatial domain, the kind of operation that we have done is basically a high pass filtering operation. So, now first of all, we will consider the smoothing frequency domain filters or low pass filters in the frequency domain. Now, as we have already discussed that edges as well as sharp transitions like noises, they lead to high frequency components in the image. And if we want to reduce these high frequency components, then the kind of filter that we have to use is a low pass filter, where the low pass filter will allow the low frequency components of the input image to be passed to the output, and it will cut off the high frequency components of the input image, which will not be passed to the output. So, our basic model for this filtering operation will be like this, that we will have the output in the frequency domain, which is given by G u v, which is equal to H u v multiplied by F u v, where this F u v is the Fourier transform of the input image, and we have to select a proper filter function H u v, which will attenuate the high frequency components, and it will let the low frequency components to be passed to the output. Now, here we will consider an ideal low pass filter, where we will assume the ideal low pass filter to be like this, that H u v is equal to 1 if d u v, where d u v is the distance of the point u v in the frequency domain from the origin of the frequency rectangle. So, if d u v is less than or equal to some value, say d 0, then H u v will be equal to 1, and this will be equal to 0 if the distance from the origin of the point u v is greater than d 0. So, this clearly means that if I multiply f u v with such an h u v, then all the frequency components lying within a circle of radius d 0 will be passed to the output, and all the frequency components lying outside this circle of radius d 0 will not be allowed to be passed to the output. Now, if the Fourier transform f u v is centered is the centered Fourier transform, that means the origin of the Fourier transform rectangle is set at the middle of the rectangle, then this d u v, the distance value, is simply computed as u minus m by 2 square plus v minus n by 2 square square root of this, where we are assuming that we have an image of size m by n. So, for an m by n image size, d u v will be computed like this if the Fourier transform f u v is the centered Fourier transformation. A plot of this kind of function is like this. So, here you find that the left hand side shows the perspective plot of such an ideal filter, whereas on the right hand side we just show the cross section of such an ideal filter. And in such cases, we define a cutoff frequency of the filter to be the point of transition between h u v equal to 1 and h u v equal to 0. So, in this particular case, this point of transition is the value d 0. So, we consider d 0 to be the cutoff frequency of this particular filter. Now, it may be noted that such a sharp cutoff filter is not realizable using the electronic components. However, using software, using computer program, it is different, because we are just letting some values to be passed to the output and we are making the other values to be 0. So, this kind of ideal low pass filter can be implemented using software, whereas using electronic components we are not able to implement such ideal low pass filters. So, a better approximation of this is a filter which is called a Butterworth filter. So, a Butterworth filter or Butterworth low pass filter is the response, the frequency response of this is given by h u v is equal to 1 upon 1 plus d u v by d 0 to the power 2 n. So, this is a Butterworth filter of order n. The response of the plot of such a Butterworth filter is shown here. So, here we have shown the Butterworth filter, the perspective plot of the Butterworth filter, and on the right hand side we have shown the cross section of this Butterworth filter. Now, if I apply the ideal low pass filter and the Butterworth filter on an image, let us see what will be the kind of the output image that we will get. So, in all these cases we assume that first we take the Fourier transform of the image, then multiply that Fourier transformation with the frequency response of the filters, then whatever the product that we get, we take the inverse Fourier transformation of this to obtain our processed image in the spatial domain. So, here we use two images for test purpose. On the left hand side we have shown an image without any noise, and on the right hand side we have shown an image where we have added some amount of noise. Then if I process that image using the ideal low pass filter and using the Butterworth filter, the top row shows the results with ideal low pass filter when the image is without noise, and the bottom row shows the result by applying the Butterworth filter again when there is no noise contamination with the image. Here you find, as the top row shows, that if I use the ideal low pass filter for the same cutoff frequency say 10, the blurring of the image is very high compared to the blurring which is introduced by the Butterworth filter. If I increase the cutoff frequency, when I go for cutoff frequency of 20, in that case you find that in the original image, in the ideal low pass filtered image, the image is very sharp, but the disadvantage is that if you simply look at these locations, say along these locations, you find that there is some ringing effect. That means there are a number of lines, undesired lines, which are not present in the original image. Same is the case over here. So, the Butterworth filter, Butterworth Lowpass filter, it introduces the ringing effect which are not visible in case of Butterworth filter. Now, the reason why the ideal Lowpass filters introduces the ringing effect is that we have seen that for an ideal Lowpass filter, in the frequency domain, the ideal Lowpass filter response was something like this. So, if I plot u versus h u, this was the response of the ideal Lowpass filter. Now, if I take the inverse Fourier transform of this, corresponding h x will have a function of this form, like this. So, here you find that there is a main component which is the central component, and there are other secondary components. Now, the spread of this main component is inversely proportional to d0, which is the cutoff frequency of the ideal filter, ideal Lowpass filter. So, as I reduce d0, this spread is going to increase, and that is what is responsible for more and more blurring effect of the smoothed image. Whereas, all the secondary components, the number of these components again over an unit length is again an inverse function, inversely proportional to this cutoff frequency d0, and these are the ones which are responsible for ringing effect. When I use Butterworth filter, the outputs that we have shown here using the Butterworth filters, these outputs are obtained using Butterworth filter of order 1, that is value of n is equal to 1. So, Butterworth filter of order 1 does not lead to any kind of ringing effect, whereas, if I go for Butterworth filter of higher order, that may lead to the ringing effect. In the same manner, we can also go for Gaussian Lowpass filter, and we have already said that for a Gaussian Lowpass filter, the filter response h u v is given by e to the power minus d square u v upon 2 sigma square, and if I allow sigma to be equal to the cutoff frequency say d0, then this h u v, the filter response, will be e to the power minus d square u v upon 2 d naught square. Now, if I use such a Gaussian Lowpass filter for filtering operation, and as we have already said, the inverse Fourier transform of this is also Gaussian in nature. So, using the Gaussian filters, we will never have any ringing effect in the processed image. So, this is the kind of the Lowpass filtering operation or smoothing operations in the spatial domain that we can have. We can also have the high frequency operation or sharpening filters in the frequency domain. So, as Lowpass filters give the smoothing effect, the sharpening effect is given by the Highpass filter. Again, we can have the ideal Highpass filter, we can have the Butterworth Highpass filter, we can also have the Gaussian Highpass filter. So, just in the reverse way, we can define an ideal Highpass filter as, for an Highpass filter, the ideal Highpass filter will be simply h u v is equal to 0 if d u v is less than or equal to d 0, and this will be equal to 1 if d u v is greater than d 0. So, this is the ideal Highpass filter. Similarly, we can have Butterworth Highpass filter, where h u v will be given by the expression 1 upon 1 plus d 0 by d u v to the power 2 n and we can also have the Gaussian high pass filter, which is given by h u v is equal to 1 minus e to the power minus d square u v upon 2 d 0 square. And you find that in all these cases, the response, the frequency response of an high pass filter, if I write it as A h h p, is nothing but 1 minus the response of a low pass filter. So, the high pass filter response can be obtained by the low pass filter response, where the cutoff frequencies are same. Now, using such high pass filters, the kind of result that we can obtain is given here. So, this is the ideal high pass filter response, where the left hand side gives you the perspective plot and the right hand side gives you the cross section. This shows the Butterworth filter perspective plot as well as cross section of a Butterworth filter of order 1. And if I apply such high pass filters to the image, to the same image, then the result that we obtain is something like this. So, here on the left hand side, this is the response of an ideal high pass filter. On the right hand side, we have shown the response of a Butterworth high pass filter, and in both these cases the cutoff frequency was taken to be equal to 10. This one, where the cutoff frequency was taken to be equal to 50, and if you closely look at the ideal filter output, here again you find that you can obtain, you can find that there are ringing effects around this boundaries, whereas in case of Butterworth filter there is no ringing effect. And again we said that this is a Butterworth filter of order 1. If I go for higher order Butterworth filters, that also may lead to ringing effects. Whereas, if I go for a high pass filter which is Gaussian high pass filter, the Gaussian high pass filter does not lead to any ringing effect. So, using these high pass filters, I can go for smoothing operation. Using the low pass filters, I can go for the smoothing operation, and using the high pass filters, I can go for image sharpening operation. The same operation can also be done using the Laplacian in the frequency domain. It is simply because if I take the Laplacian of a function, if for a function f x y, I get the corresponding frequency domain, say f u v, the corresponding Fourier transform, then the Laplacian operator, if I perform del square f x y and take the Fourier transform of this, this will be nothing but, it can be shown, it will be equal to minus u square plus v square into f u v. So, using this operation, if I consider say h u v is equal to minus u square plus v square, and using this as a filter, I filter this f u v, and after that I compute the inverse Fourier transformation, then the output that we get is nothing but a Laplacian operated output, which will obviously be an enhanced output. Another kind of filtering that we have already done during in connection with our spatial domain operation, that is high boost filtering. So, there we have said that in spatial domain the high boost filtering operation, the high boost filtering output f x y, if I represent this as f h b x y, is nothing but a into f x y minus f l p x y, and which is can be represented as a minus 1 into f x y plus f high pass filtered output x y. In the frequency domain, the corresponding operation, the corresponding filter can be represented by h b u v is equal to a minus 1 plus high pass filter u v. So, this is what is the high boost filter response in the frequency domain. So, if I apply this high boost filter to an image, the kind of result that we get is something like this, where again on the left hand side is the original image and on the right hand side it is the high boost filtered image. Now, let us consider another very interesting filter which we call as homomorphic filter. Homomorphic filter. The idea aims from one of the earlier discussions, where we have said that the intensity at a particular point in the image is a product of two terms. One is the illumination term, other one is the reflectance term. That is f x y, we have earlier said that it can be represented by an illumination term I x y multiplied by r x y, where r x y is the reflectance term. Now, coming to the corresponding frequency domain, because this is a product of two terms, one is the illumination, other one is the reflectance, taking the Fourier transform directly on this product is not possible. So, what we do is we define a function say z x y, which is logarithm of f x y, and this is nothing but logarithm of I x y plus logarithm of r x y. And if I compute the Fourier transform, then the Fourier transform of z x y will be represented by z u v, which will have two components f I u v plus f r u v, where this f I u v is the Fourier transform of ln I x y and f r u v is the Fourier transform of ln r x y. Now, if I define a filter say h u v and apply this filter on this z u v, then the output that I get is say s u v, which is equal to h u v times z u v, which will be nothing but h u v times f I u v plus h u v times f r u v. Now, taking the inverse Fourier transform, I get s x y is equal to I dash x y plus r dash x y, and finally, I get g x y, which is nothing but e to the power s x y, which is nothing but e to the power I dash x y into e to the power r dash x y, which is nothing but I 0 x y into r about x y. So, the first term is the illumination component and second term is the reflectance component. Now, because of this separation, it is possible to design a filter which can enhance the high frequency components and it can attenuate the low frequency components. Now, it is generally the case that in an image the illumination component leads to low frequency components because illumination is slowly varying, whereas the reflectance component leads to high frequency components, particularly at the boundaries of two reflecting objects. As a result, the reflectance term leads to high frequency components and illumination term leads to low frequency components. So, now if we define a filter like this, a filtered response like this, and here if I say that I will have say gamma h greater than 1 and gamma L less than 1, this will amplify all the high frequency components, that is the contribution of the reflectance, and it will attenuate the low frequency components, that is contribution due to the illumination. Now, using this type of filtering, the kind of result that we get is something like this. Here on the left hand side is the original image and on the right hand side is the enhanced image. And if you look in the boxes, you find that many of the details in the boxes which are not available in the original image is now available in the enhanced image. So, using such homomorphic filtering, we can even go for this kind of enhancement where the illumination, the contribution due to illumination will be reduced. So, even in the dark areas we can take out the details. So, with this we come to an end to our discussion on image enhancements. Now, let us go to some questions of our today's lecture. The first question is, a digital image contains an unwanted region of size 7 pixels. What should be the smoothing mask size to remove this region? Why Laplacian operator is normally used for image sharpening operation? Third question, what is unsharp masking? Fourth question, give a 3 by 3 mask for performing unsharp masking in a single pass through an image. Fifth, state some applications of first derivative in image processing. Then what is ringing? Why ideal low pass and high pass filters lead to ringing effects? How does blurring vary with cutoff frequency? Does Gaussian filter lead to ringing effect? Give the transfer function of a high boost filter, and what is the principle of homomorphic filter? Thank you.